Imagine you are standing on a beach. The sand stretches out beneath your feet, warm and familiar, and ahead of you lies the ocean, vast and blue and seemingly endless. Now imagine someone tells you that you need to cross that ocean, not in a boat, not in a plane, but by swimming. Every single stroke, every single breath, every single moment of exhaustion and fear and doubt, you must push through. Because on the other side of that ocean lies something extraordinary, something that could change everything we know about our existence. You would look at that ocean and feel a knot form in your stomach, right? You would feel the sheer impossibility of it pressed down on your chest like a weight. Now I want you to take that feeling, that sinking, suffocating realization of impossible distance, and I want you to multiply it by a number so large that your brain physically cannot process it. Because that ocean, as vast and terrifying as it seems, is nothing. It is a puddle. It is a drop. It is less than a grain of sand compared to the desert that lies between us and the nearest star. And today, we are going to talk about that desert. We are going to talk about the gap, the void, the incomprehensible chasm of nothingness that separates our tiny little world from the closest pinprick of light in our night sky. And I promise you, by the time we are done, you will never look at the stars the same way again. Before we dive into the abyss, let me tell you what we are going to explore today. Because this is not just a video about a number. This is not just someone telling you that a star is far away and expecting you to nod and move on. No. Today we are going to systematically dismantle every intuition your brain has about distance. We are going to start with what you think you know, and then we are going to tear it apart layer by layer until you are staring into the raw, unfiltered truth of cosmic distance. We will talk about light itself, the fastest thing in the universe, and why even light finds this journey a marathon. We will meet the star that sits closest to us, and we will discover it is not just one star, but an entire system with planets that might, just might, harbour the conditions for life. We will calculate, in brutal and unforgiving detail, exactly how long it would take to reach that star with every mode of transportation humanity has ever invented. We will explore the void itself, the terrifying emptiness between here and there, a stretch of nothing so profound that it challenges the very meaning of the word empty. We will examine every single idea humanity has ever proposed to cross this gap, from nuclear explosions to laser beams to ships that carry entire generations of humans born and dying in the darkness between stars. And finally, we will confront the philosophical horror and the strange, unexpected beauty of what this distance means for us as a species, for our future, for our place in the cosmos, and for the biggest question of all, whether we are truly, fundamentally, cosmically alone. So settle in. This is going to be a long journey, and that in itself is perhaps the most fitting metaphor I could offer for what we are about to discuss. Let me start with a question that sounds simple, but is actually one of the most deceptive questions in all of science. How far away is the nearest star? If you have any passing interest in astronomy, you probably know the answer. It is about 4.24 light-years away. The star is called Proxima Centauri, and it sits at a distance of roughly 4.24 light-years from Earth. There, question answered. Video over. Except no, because that answer, those few words, 4.24 light-years, they are perhaps the most misleading collection of syllables in the entire human language. They sound manageable. They sound almost cozy. 4. That is a small number. You can count to 4 on one hand. Light years? Well, light is fast, right? So a light year cannot be that big. The whole thing sounds like it might be a pleasant road trip, maybe a long weekend if you drive fast enough. And this is exactly the problem. This is the trap. This is where your brain, that magnificent 3-pound organ that can compose symphonies and split atoms and fall in love, this is where your brain completely and utterly fails you. Because 4.24 light-years is not a small distance. It is not a medium distance. It is not even a large distance. It is a distance so monumentally, incomprehensibly, absurdly vast that every analogy I am about to give you will feel insufficient. Every comparison will fall short. Every attempt to make you truly feel this distance in your gut will be an approximation of the truth, because the truth is something the human mind was simply not built to hold. Let me tell you why your brain fails at this. It is not your fault. It is evolution. Your brain evolved on the plains of Africa somewhere between 200,000 and 300,000 years ago. The problems it needed to solve were immediate, tangible, and relatively small scale. How far away is that predator? Can I throw this rock far enough to hit that animal? How many days of walking until I reach the next water source? The largest distances your ancient ancestors ever needed to comprehend were maybe a few hundred kilometers, maybe 1,000 if they were exceptionally well-traveled, and so your brain developed an intuition for distance that works beautifully at this scale. You can look at a football field and feel how big it is. You can imagine the drive from one city to another and have a gut sense of the time and distance involved. You can even stretch your imagination to encompass the distance from one country to another, though it starts getting fuzzy. But that is where it stops. Your brain has a distance limit, a built-in ceiling above which numbers become abstract, meaningless, just sounds without substance. And the distances in space are so far above that ceiling that they might as well be in a different dimension of reality. Here is an example that demonstrates this beautifully. I want you to think about the difference between 1 million and 1 billion. Most people, if you ask them, will tell you that a billion is quite a bit more than a million. It is bigger, sure, a lot bigger. But their gut feeling is that it is, maybe 10 times bigger, or maybe 100 times bigger. The truth is that 1 billion is 1,000 times bigger than 1 million. And here is how you can feel that difference. 1 million seconds is approximately 11.5 days. If you started counting seconds right now, 1 per second, you would reach 1 million in less than 2 weeks. 1 billion seconds is approximately 31.5 years. The same count, 1 second at a time, would take you from being a newborn baby to being older than most PhD students. That is the difference, 11 days versus 31 years. And yet most people's brains process million and billion as being in roughly the same neighborhood. Now here is the terrifying part. The distances in space do not deal in millions or billions. They deal in trillions. And the difference between a billion and a trillion is the same 1,000-fold jump. If a billion seconds is 31 years, a trillion seconds is 31,000 years. That takes you back to a time before agriculture, before civilization, before the first city was ever built. And the distance to the nearest star? It is measured in tens of trillions of kilometers. Your brain has no hope, no chance, no framework for processing a number like that. And that is exactly why we need to build one from scratch today. Let us start building that framework right now. Let us start with distances you know, and then climb the ladder rung by rung until we reach the terrifying top. The first rung is easy. The distance from New York City to London is approximately 5,500 kilometers. You probably know roughly how far that is. You might have flown it. It takes about 7 hours in a commercial airplane. It is a distance your brain handles with complete comfort. Now let us go up one rung. The distance from the Earth to the Moon is approximately 384,400 kilometers. That is about 70 times the distance from New York to London. When the Apollo astronauts made this journey, it took them about 3 days. This is a distance that starts to stretch your intuition a little bit, but you can still kind of feel it. You can imagine 3 days of travel. You have been on long trips before. It is not comfortable, but it is comprehensible. Now here is where it starts getting interesting. The distance from the Earth to the Sun is approximately 150 million kilometers. Astronomers call this 1 astronomical unit, or 1 AU, and it is a fundamental measuring stick in our solar system. This distance is about 390 times the distance from Earth to the Moon. Light, travelling at 300,000 kilometers per second, takes 8 minutes and 20 seconds to cross this distance. Think about that. The light that warms your face when you step outside has been travelling for over 8 minutes since it left the surface of the sun. If the sun suddenly vanished right now, you would not know for 8 minutes. You would continue feeling its warmth, seeing its light, for 8 minutes after it ceased to exist. The distance to the sun is already beyond comfortable human intuition, but with effort, with analogies, you can sort of wrap your head around it. It is far but knowable. Let us keep climbing. The distance from Earth to Mars at its closest approach is about 55 million kilometers, and at its farthest, about 400 million kilometers. On average, let us call it about 225 million kilometers. This is why a trip to Mars takes roughly 7 months with current technology. 7 months of hurtling through the void at tens of thousands of kilometers per hour, and you will reach our neighboring planet. This is our current frontier. This is the edge of where humanity is actively planning to send people. It is far. It is dangerous. It is at the absolute ragged edge of what our technology can achieve for crewed missions. And yet, compared to what comes next, Mars is in our backyard. Mars is a neighbour whose fence you could lean over. Jupiter is approximately 778 million kilometers from the Sun, or about 5.2 AU. The Voyager 1 spacecraft, travelling at tremendous speed, took about 2 years to reach Jupiter after its launch in 1977. Saturn is about 1.4 billion kilometers, Uranus about 2.9 billion, and Neptune about 4.5 billion. And then there is Pluto, that distant, icy, demoted little world at the edge of our planetary neighbourhood, sitting at an average distance of about 5.9 billion kilometers from the Sun. The New Horizons spacecraft, which was launched with the fastest launch speed ever achieved by a human-made object at the time, took 9.5 years to reach Pluto. 9.5 years of travel to reach a world that is still, cosmically speaking, right next door to us. It is still inside our solar system. It is still orbiting our sun. It is still, in the grand scheme of things, home. Now I need you to pay very close attention to what I am about to say, because this is where the ladder does not just go up another rung. This is where the ladder essentially teleports you to the top of Mount Everest in a single step. Everything I have described so far, the Moon, the Sun, Mars, Jupiter, Pluto, all of it exists within our solar system. Our solar system, as vast as it may seem with its billions of kilometers, is a tiny bubble in space. And the nearest star, Proxima Centauri, is outside that bubble. Way, way, way outside that bubble. The distance to Proxima Centauri is approximately 40.14 trillion kilometers. Let me write that out so it does not just slide past you as another number. That is 40,000 billion kilometers. Or in another way, that is approximately 268,000 times the distance from the Earth to the Sun. Or if you prefer, it is approximately 6,800 times the distance from the Sun to Pluto. Think about what that means. That distance from the Sun to Pluto, the one that took New Horizons 9.5 years to cross, you would need to make that journey 6,800 times back to back to reach the nearest star. You would need to stack that 9.5-year journey end to end almost 7,000 times. That is not a rung on a ladder. That is a chasm. That is an abyss. That is a gap so profound that it makes everything else we have talked about look like stepping over a crack in the sidewalk. And you need to feel this difference. Truly feel it. So let me give you the scale models that will break something in your brain. I want them to break something, because only when your old framework shatters can a new, more accurate one take its place. Imagine you take the sun and you shrink it down to the size of a basketball. A standard basketball, the kind you would find in any gym. In this model, the Earth would be a tiny grain of sand about 26 meters away from that basketball. 26 meters, about the length of a swimming pool. And in this model, how far away do you think the nearest star would be? Another basketball representing Proxima Centauri would need to be placed approximately 6,500 kilometers away. 6,500 kilometers. If your basketball sun is in New York City, your nearest star basketball is in Hawaii. If your basketball sun is in London, your nearest star is somewhere past Baghdad. Between them? Nothing. Absolutely nothing. Just 6,500 kilometers of empty floor. No other basketballs, no other grains of sand, just void. That is the scale of what we are dealing with. Here is another one. Imagine you take the distance between the Earth and the Sun, those 150 million kilometers, and you shrink it down to 1 inch. 1 inch. The width of your thumb. In this model, the nearest star would be 4.3 miles away. 4.3 miles of empty space, with your thumb width representing the entire enormous distance from the Earth to the Sun. And between that thumb width and the point 4.3 miles away, almost nothing. A few specks representing the outer planets, the Kuiper belt, maybe some whispers of the Oort cloud, but effectively empty space. Empty, cold, dark, silent space. Or try this one. If the sun were a grain of sand sitting on a table in front of you in Lahore, Pakistan, and you wanted to place another grain of sand to represent the nearest star at the correct scale, you would need to place that grain of sand in London, England. Lahore to London, 2 grains of sand separated by over 6,000 kilometers. And the space between them? Nothing that you would notice at this scale. The entire rest of our solar system, all those planets, all those moons, all those asteroids and comets, would be contained within a few meters of that first grain of sand. The rest of the distance, all 6,000 plus kilometers of it, would be absolute emptiness. This is what we are up against. This is the gap. And I have not even started telling you the worst parts yet. Let me introduce you to the concept that makes this whole picture even more stark. Let us talk about light and what a light year actually means in terms you can feel. Light is the fastest thing in the universe. Nothing that carries information can travel faster than light. This is not a technological limitation. This is not something we will engineer our way past with better engines. This is a fundamental law of physics, woven into the very fabric of space-time itself. The speed of light is 299,792 kilometers per second. Per second. In a single second, a beam of light could circle the entire Earth 7.5 times. In the time it takes you to snap your fingers, light has wrapped around our planet 7 times and is halfway through its 8th lap. In 1 minute, light covers approximately 18 million kilometers. That is far enough to travel from the Earth to the Moon and most of the way back 47 times. In 8 minutes and 20 seconds, light covers the distance from the Sun to the Earth. That is 150 million kilometers in about the time it takes to brew a cup of tea. In about 5.5 hours, light reaches Pluto, crossing those 5.9 billion kilometers. In 1 year, light covers approximately 9.46 trillion kilometers. That is a light year, 9.46 trillion kilometers, and the nearest star is 4.24 of those. 4.24 times 9.46 trillion. That is where we get our 40 trillion kilometers. Now here is what this means in human terms, and I want you to really sit with this. If you could somehow see the nearest star right now, if you had a telescope powerful enough to watch events unfold on a planet orbiting Proxima Centauri, you would not be seeing what is happening there now. You would be seeing what happened 4 years and 3 months ago. The light arriving at your telescope tonight left Proxima Centauri in early 2022. If an alien civilization on Proxima Centauri be exploded a nuclear weapon on their surface right now, at this very moment, we would not see the flash for over 4 years. If we sent a radio signal to them right now, travelling at the speed of light, it would arrive in about 4 years and 3 months. If they immediately sent a reply, we would receive it about 8.5 years after we sent our original message. 8.5 years for a simple hello and response. And this is with light, the fastest possible messenger in the universe. Everything else, every rocket, every spacecraft, every projectile humanity has ever launched, is laughably, heartbreakingly slower. Now, if you are finding this journey through cosmic distances as mind-bending as I think you are, take a moment right now and hit that like button. And if you have not already, subscribe to this channel and turn on the notification bell. Trust me, the deeper we go into this topic today, the more your mind is going to be blown. And I want you here for every single revelation that is coming. Drop a comment right now telling me what you think so far. Do you think humanity will ever cross this gap? Keep that answer in mind, because by the end of this video, you might change it. Now let us keep going, because we have barely scratched the surface. Let me now take you through an exercise that is going to be painful, but necessary. We are going to calculate, with cold mathematical precision, exactly how long it would take to reach Proxima Centauri using various modes of transportation. And I want you to watch these numbers carefully, because each one is going to be worse than the last, and even the best one is going to make you want to lie down. Let us start with walking. The average human walking speed is about 5 kilometers per hour. You know this speed. You feel it every day when you walk to the store, to school, to work. It is a comfortable, familiar speed. At 5 kilometers per hour, the time to walk to Proxima Centauri would be approximately 8 billion years. 8 billion years. The Earth itself is only about 4.5 billion years old. The Sun has only existed for about 4.6 billion years. If you had started walking to Proxima Centauri at the moment our solar system was forming from a cloud of gas and dust, 4.6 billion years ago, you would be barely past the halfway point. You would still have billions of years of walking ahead of you. The dinosaurs would have evolved and gone extinct behind you, and you would not have even noticed, because you would still be walking, one foot in front of the other, through the endless dark void between stars. Walking is out. Obviously, but I needed you to feel the absurdity of the starting point so that what comes next has proper context. Let us get in a car. A fast car. Let us say you are driving at 100 kilometers per hour on a perfectly straight, perfectly smooth highway that extends from Earth to Proxima Centauri. At 100 kilometers per hour, the drive would take approximately 45 million years. 45 million years. Let me put that in perspective. The asteroid that killed the dinosaurs struck the Earth about 66 million years ago. If a Tyrannosaurus Rex had somehow gotten into a car and started driving toward Proxima Centauri on the day before the asteroid hit, the T-Rex would still not have arrived. It would still be out there somewhere in the interstellar void, with about 21 million years of driving left to go, 66 million years of non-stop driving, and the destination is still not in sight. The car is faster than walking, sure, but in the context of interstellar distances, it might as well not be. What about an airplane? A commercial jet flies at about 900 kilometers per hour. That is 9 times faster than our car. At airplane speed, the trip would take approximately 5 million years. 5 million years. The entire genus Homo, the lineage that includes modern humans and all our close extinct relatives, has only existed for about 2 to 3 million years. You would need to fly for roughly twice the entire duration of human evolutionary history to reach the nearest star. Imagine every moment of human evolution, from the first tool users to the builders of the pyramids to the astronauts who walked on the moon, and then double it. That is your flight time. I hope you brought a long book. Now let us try something faster. A bullet. The fastest rifle bullets travel at about 1,700 meters per second, or roughly 6,100 kilometers per hour. A bullet is fast. A bullet is so fast you cannot see it. A bullet crosses a football field before you can blink. At bullet speed, the journey to Proxima Centauri would take approximately 750,000 years. 750,000 years. Homo sapiens, our specific species, has existed for roughly 300,000 years. A bullet fired when the first anatomically modern humans appeared in Africa would have covered less than half the distance by now. It would still be out there screaming through the void at 6,000 kilometers per hour, with hundreds of thousands of years of travel still ahead. And a bullet is fast. A bullet is one of the fastest things in our everyday experience. But space does not care about our everyday experience. Let us jump to something much faster. Let us talk about the Parker Solar Probe, which as of its most recent perihelion passages has achieved speeds of approximately 635,000 kilometers per hour. This is the fastest speed any human-made object has ever achieved. It is mind-bogglingly fast. At this speed you could circle the Earth in about 4 minutes. You could get from New York to Los Angeles in about 23 seconds. This is the absolute pinnacle of human velocity. At Parker Solar Probe speed, the journey to Proxima Centauri would take approximately 7,200 years. 7,200 years. Let that register. Our fastest technology, the absolute peak of human engineering and orbital mechanics, would need over 7 millennia to reach the nearest star. 7,000 years ago, humanity was just beginning to figure out agriculture in some parts of the world. Writing had not been invented. The wheel had not been invented. The pyramids would not be built for another 2,000 years. If ancient Sumerians had somehow launched a Parker Solar Probe at Proxima Centauri at the dawn of civilization, it would still have about 2,000 years of travel time remaining. We would still be waiting. But wait. Let us look at the spacecraft we have actually sent in the direction of interstellar space. Voyager 1, that legendary little spacecraft launched in 1977, is currently the farthest human-made object from Earth. It has been traveling for over 47 years. It is moving at approximately 61,000 kilometers per hour. It is currently about 24 billion kilometers from Earth. That sounds impressive, right? 24 billion kilometers? That is far. That is way past Pluto. That is in interstellar space, technically. But here is the gut punch. 24 billion kilometers is approximately 0.06% of the distance to Proxima Centauri. Let me say that again. After 47 years of travel, at 61,000 kilometers per hour, Voyager 1 has covered 0.06% of the distance to the nearest star. It has covered so little of the journey that it is essentially still standing at the starting line. If the distance to Proxima Centauri were a marathon, 26.2 miles, Voyager 1 has travelled about 83 feet. Not miles. Feet after 47 years. At Voyager 1's current speed, it would take approximately 73,000 years to reach Proxima Centauri. 73,000 years. 73,000 years ago, Neanderthals still roamed Europe. Modern humans were just beginning to migrate out of Africa. We had not invented agriculture, or cities, or language as we know it, or anything remotely resembling civilization. If Neanderthals had launched Voyager 1 73,000 years ago, it would be arriving at Proxima Centauri roughly now. The entire sweep of human civilization, everything we have ever built or done or dreamed, fits comfortably inside the travel time of our farthest spacecraft to the nearest star. New Horizons, which was launched at the fastest launch speed of any spacecraft at the time, about 58,000 kilometers per hour, and has since slowed to roughly 50,000 kilometers per hour, would fare no better. At its current speed, New Horizons would need approximately 78,000 years to reach Proxima Centauri. These are our best spacecraft. These are the pinnacles of human space exploration, the furthest reaching arms we have ever extended into the cosmos. And they are pathetically, heartbreakingly inadequate for interstellar travel. Now let me put all of these speeds side by side so you can see the full picture. Walking, 8 billion years. Driving, 45 million years. Flying commercial, 5 million years. Bullet, 750,000 years. Voyager 1, 73,000 years. Parker Solar Probe, 7,200 years. Do you see the pattern? Even as we jump to dramatically faster speeds, the numbers remain incomprehensibly huge. We went from walking speed to the fastest human-made object, an increase in speed of over 100,000 times, and we only brought the travel time down from 8 billion years to 7,000 years. That is still 7,000 years. That is still longer than recorded human history. And that is the crux of the problem. The distance is so vast that even enormous improvements in speed barely dent the travel time. So what speed would we actually need? Let us do the math. If we wanted to reach Proxima Centauri in a single human lifetime, say 100 years, we would need to travel at roughly 4% of the speed of light. 4% of light speed is about 43 million kilometers per hour. Our fastest spacecraft travels at 635,000 kilometers per hour. We would need to go approximately 8 times faster than the fastest thing we have ever built. That is for a 100-year journey. If we wanted to get there in 50 years, a more reasonable human timescale, we would need about 8% of the speed of light, roughly 86 million kilometers per hour, about 135 times faster than Parker Solar Probe. And if we were truly ambitious and wanted to make the trip in just 10 years, we would need to travel at roughly 42% of the speed of light, about 450 million kilometers per hour, over 700 times faster than anything humanity has ever created. These are the numbers. These are the cold, hard, mathematical requirements for interstellar travel, and every single one of them is currently beyond our reach. Not slightly beyond. Not give us a few more years and we will figure it out beyond. They are beyond in a way that requires fundamental leaps in technology that we do not yet know how to make. This is the gap. This is what worse than you imagine means. And we are only getting started. Let us now turn our attention to the star itself, because if we are going to spend all this time talking about how impossibly far away it is, we should at least know what is actually out there waiting at the end of that impossible journey. And what is out there is far more interesting than most people realize. When I say the nearest star, most people picture a single lonely light in the darkness. But the truth is more complex and more beautiful. The nearest star system to our Sun is not a single star at all. It is a triple star system called Alpha Centauri, and it contains 3 distinct stellar objects, each with its own personality, its own story, and its own potential significance for the future of humanity. The first and brightest member of this system is Alpha Centauri A. This star is remarkably similar to our own Sun. It is a yellow dwarf star, classified as spectral type G2V, which is the exact same classification as the Sun. It is slightly larger, with about 1.1 times the Sun's mass and about 1.22 times its radius. It is about 1.5 times more luminous than our Sun. If you were standing on a planet orbiting Alpha Centauri A, you would see a star that looked very much like the one that warms our own world, just a bit bigger and brighter. There is something profoundly poignant about this. Our nearest stellar neighbour in the universe is almost a twin of our own star. It is like looking across that impossible void and seeing a mirror. The second member is Alpha Centauri B. This star is slightly smaller and cooler than the Sun, classified as a K1V type, making it an orange dwarf. It has about 90% of the Sun's mass and about 86% of its radius. It shines at about half the Sun's luminosity. it is still a perfectly respectable star, entirely capable of warming planets and potentially supporting conditions for life. Alpha Centauri A and B orbit each other in a gravitational dance that takes approximately 80 years to complete. At their closest approach, they are about 11 AU apart, roughly the distance from the Sun to Saturn. At their farthest, they separate to about 36 AU, similar to the distance from the Sun to Pluto. This binary pair has been dancing together for billions of years, two stellar partners waltzing through the galaxy in their slow, majestic orbit. And then there is the third member, the one that matters most for our story. Proxima Centauri. This is the actual nearest star to our solar system, edging out its two larger companions by a slim margin. Proxima is a red dwarf, classified as M5, 5V, and it is tiny by stellar standards. It has only about 12% of the Sun's mass and roughly 15% of its radius. If you could place it next to the Sun, it would look like a marble next to a bowling ball. Its surface temperature is about 3042 Kelvin, compared to the Sun's 5778 Kelvin. It is a cool, dim, angry little star. And when I say dim, I mean profoundly dim. Proxima Centauri shines with only about 0.17% of the Sun's luminosity. That means it puts out about 1/600th of the light our Sun does. Despite being the closest star to Earth, you cannot see it with the naked eye. Think about that. The nearest star in the entire universe, the closest nuclear furnace to our own, is so faint that on a clear night, when you look up at the thousands of stars visible to the naked eye, the nearest one is not among them. It is too dim to see without a telescope. The stars you see twinkling above you are almost all much farther away, some hundreds or thousands of light years distant. They are just much bigger and brighter, so they outshine our little neighbour. Proxima Centauri was not even discovered until 1915, when the astronomer Robert Innes at the Union Observatory in Johannesburg, South Africa, noticed this faint red star and determined that it had the largest known proper motion of any star, suggesting it was very close. It was named Proxima, meaning nearest in Latin, and it has held that title ever since. Proxima Centauri orbits the Alpha Centauri A and B pair at a vast distance, approximately 13,000 AU from the binary, which is about 1/5 of a light year. Its orbital period around the binary is estimated at somewhere around 500,000 to 550,000 years. This is so long that astronomers actually debated for decades whether Proxima was truly gravitationally bound to the system or just passing through. Recent measurements have confirmed that it is indeed bound, making it a true, if distant, member of the family. But there is something important about Proxima that we need to discuss. Something that makes it both fascinating and terrifying. Proxima Centauri is what astronomers call a flare star. It is prone to sudden, violent outbursts of energy. These stellar flares can increase the star's brightness by enormous factors in a matter of minutes. In 2018, astronomers detected a superflare from Proxima Centauri that briefly made it 100 times brighter in ultraviolet light. Imagine that. You are on a planet orbiting this star, and one day, without warning, your sun suddenly becomes 100 times more intense. The radiation that slams into any orbiting planet during these events is staggering. It would strip atmospheres, sterilize surfaces, and make life as we know it extremely difficult to maintain. Proxima has these flares regularly, sometimes multiple times per day for smaller events. It is not a gentle star. It is a tempestuous, unpredictable neighbour that smiles at you one moment and screams at you the next. And yet, despite all of this, in 2016, something extraordinary was discovered, something that changed the entire conversation about interstellar travel and the search for life beyond Earth. Astronomers using the European Southern Observatory's telescopes announced the discovery of a planet orbiting Proxima Centauri in its habitable zone. They called it Proxima Centauri b, and the world of astronomy has not been the same since. Proxima Centauri b is a rocky planet with a minimum mass of about 1.17 Earth masses. It orbits its star at a distance of approximately 7.5 million kilometers, which is only about 5% of the distance from Earth to the Sun. At first glance, this sounds like it should be a scorching hellscape, a world baked by the heat of its star at such close proximity. But remember, Proxima Centauri is extremely dim. It puts out a tiny fraction of the Sun's energy, and so the habitable zone, the region around a star where liquid water could potentially exist on a planet's surface, is much closer in for a red dwarf than it is for a Sun-like star. At 7.5 million kilometers from Proxima Centauri, the planet receives about 65 to 70% of the energy that Earth receives from the Sun. That puts it right in the sweet spot where, under the right conditions, liquid water could exist. The orbital period of Proxima b is just 11.2 days. That means a year on Proxima b lasts less than 2 weeks. While Earth lazily completes one orbit of the Sun in 365 days, Proxima b whips around its star in a week and a half. This incredibly tight orbit has consequences. Most astronomers believe that Proxima b is tidally locked to its star, meaning one side of the planet permanently faces the star, while the other side permanently faces away. Think of how the Moon always shows the same face to Earth. Proxima b likely does the same with its star. This means one hemisphere is in perpetual daylight, and the other is in perpetual darkness. The daylight side could be blisteringly hot, while the night side could be frozen solid. However, if the planet has an atmosphere, winds could potentially distribute heat from the day side to the night side, creating a region near the boundary between light and dark, the so-called terminator line, where temperatures might be moderate enough for liquid water. Some climate models suggest this could work, others are less optimistic. Then there is the flare problem. Those violent stellar flares we talked about would bombard Proxima b with intense radiation. Over billions of years, these flares could have stripped away the planet's atmosphere entirely, leaving it as a bare, irradiated rock. Or perhaps Proxima b started with a very thick atmosphere, so even after billions of years of flare erosion, enough remains to protect the surface. Or perhaps the planet has a strong magnetic field that deflects the worst of the radiation. We simply do not know yet. The planet might be a hellish, airless wasteland. Or it might be an alien world with a thick, protective atmosphere, moderate temperatures in the twilight zone, and liquid water on its surface. The difference between these two possibilities is quite literally the difference between a dead rock and a potential home for life. And we will not know which one it is until we can either examine it in extraordinary detail with future telescopes, or, dream of dreams, actually send something there to take a look. Since 2016, more planets have been found in the Proxima system. Proxima c is a candidate planet much farther from the star, possibly a super-Earth or mini-Neptune with an orbital period of about 5.2 years. It would be too cold for liquid water, but its existence tells us the system is rich in planets. Proxima d was announced in 2022 as a candidate planet extremely close to the star, with an orbital period of just 5.1 days and a minimum mass of only about a quarter of Earth's mass. If confirmed, it would be one of the lightest exoplanets ever discovered. The Proxima Centauri system is not just our nearest stellar neighbour. It is an entire planetary system, potentially with multiple worlds, at least one of which sits in the habitable zone. The universe has placed a potentially habitable planet around the nearest star to our Sun. If there is a more tantalizing cosmic coincidence than this, I cannot think of one. It is as if the universe is dangling the most irresistible bait imaginable just beyond our reach, saying, look what is right here, just a tiny 4 light years away. Don't you want to come see it? Can't you figure out how? If you were standing on the surface of Proxima b, assuming it has a surface you could stand on and an atmosphere you could see through, the view would be unlike anything you have ever experienced on Earth. Proxima Centauri, your Sun in this scenario, would appear about 3 times larger in the sky than our Sun appears from Earth, because you are so much closer to it. But it would be a deep, dull red, casting everything in a dim, ruddy glow, like a perpetual sunset that never brightens to noon. The shadows would be long and soft, and the colours of the landscape would be shifted toward reds and oranges. If Proxima flared while you were watching, the sky would suddenly blaze with light, an unexpected and terrifying brightening that could last minutes to hours before fading back to the dim red norm. Looking away from Proxima into the sky, you would see two brilliant stars close together. A dazzling pair far brighter than any star appears from Earth. These would be Alpha Centauri A and B, your nearest stellar neighbours, shining like twin beacons in the alien sky. And somewhere in that sky, in a pattern of stars that would look similar but not identical to what we see from Earth, there would be a modest, unremarkable yellowish star in the constellation we know as Cassiopeia. That star would be our Sun. You would be looking back across the gap, seeing the light that left our Sun 4 years ago, and knowing that everything you have ever known, every human being who has ever lived, every love story and war and symphony and sunset, all of it happened on a tiny rock, orbiting that one insignificant point of light. Now let us talk about what lies between us and this tantalizing destination. Because the gap between our solar system and Proxima Centauri is not just vast, it is terrifyingly empty. When you travel from one city to another on Earth, you pass through countryside, through towns, through forests and fields. There are landmarks, there are signs of life. There is air to breathe and ground beneath you and a sky above you. The journey between stars is nothing like this. It is nothing like anything you have ever experienced. It is nothing like anything any human being has ever experienced. The space between stars is the most profoundly empty environment in the known universe. Let me try to convey just how empty it is. On the surface of the Earth, every cubic centimetre of air around you contains approximately 2.5 times 10 to the 19th power molecules. That is 25 billion molecules in a space the size of a sugar cube. This air is what you breathe, what carries sound, what makes the sky blue. It is a rich, thick soup of molecules that your body and your senses are completely adapted to. Even in the best vacuum chambers we can create on Earth, there are still hundreds of millions of molecules per cubic centimetre. In low Earth orbit, where the International Space Station flies, there are still trillions of molecules per cubic centimetre in the extremely thin upper atmosphere. But in interstellar space, in the void between stars, the density drops to roughly 1 atom per cubic centimetre. One single atom in a space the size of a sugar cube. Sometimes even less. Let me try to help you feel how empty that is. Imagine you are in a room that is 10 metres by 10 metres by 10 metres. A reasonably large room, about the size of a small warehouse. On Earth, that room contains approximately 10 to the 25th power molecules, a number with 25 zeros after it. An incomprehensibly large number of tiny particles, all bouncing around, all creating the air you breathe. Now imagine that same room in interstellar space. It would contain approximately 1 billion atoms. 1 billion sounds like a lot, but remember, the room on Earth had 10 to the 25 power molecules. The interstellar version has roughly 10 to the 9th. The interstellar room is 10 to the 16th times emptier than the room on Earth. That is 10,000 trillion times emptier. If the room on Earth were the entire ocean, the interstellar room would be a fraction of a single drop. That is the void you would be travelling through, not just empty. Empty to a degree that makes our concept of empty seem laughably crowded. This interstellar medium, as it is called, is composed mostly of hydrogen and helium, with tiny traces of heavier elements. There are also incredibly fine grains of dust, microscopic particles of carbon, silicon, and iron, scattered so sparsely that the space between individual dust grains can be measured in meters or even kilometers. There are magnetic fields, incredibly weak ones, threading through the interstellar medium like invisible cobwebs. There are cosmic rays, high-energy particles moving at nearly the speed of light, remnants of distant supernovae and other violent cosmic events. And that is essentially it. That is all there is between here and there. No rest stops, no refueling stations, no landmark, no communication relays, no rescue. Nothing but atoms, dust and radiation spread so thin that empty does not even begin to describe it. The temperature of this void is approximately 2.725 Kelvin. That is 2.725 degrees above absolute zero, the lowest temperature physically possible. Absolute zero is minus 273.15 degrees Celsius, the temperature at which all thermal molecular motion ceases. The interstellar medium is just barely above this floor, warmed only by the faint glow of the cosmic microwave background radiation, the leftover heat from the Big Bang itself. If you were floating in interstellar space without a spacecraft to protect you, you would be in a darkness more complete than anything on Earth, a cold more bitter than anything Antarctica has ever known, and a silence more absolute than any vacuum chamber ever built. There would be no sound, because there is almost no medium to carry sound waves. There would be almost no light, just the distant, unchanging pinpricks of stars that barely seem to move as you travel, because they are so inconceivably far away that even moving at thousands of kilometers per hour, you would see no apparent change in their positions for years. You would be utterly, completely, fundamentally alone. And the void is not just empty, it is also dangerous. Those cosmic rays I mentioned, high-energy particles screaming through space at nearly light speed, are a serious hazard for both biology and electronics. On Earth, we are protected from the worst of cosmic radiation by two shields: the atmosphere, which absorbs and deflects most cosmic rays before they reach the surface, and the magnetosphere, the magnetic field generated by Earth's molten iron core, which deflects charged particles around the planet. In interstellar space, you have neither of these shields. The radiation dose an unprotected human would receive in interstellar space would be significantly higher than anything on Earth's surface. Over the course of a years-long or decades-long journey, this radiation would damage dinner, increase cancer risk dramatically, and potentially cause acute radiation sickness if shielding were insufficient. Electronics would also be vulnerable, with cosmic rays causing bit flips in computer memory, degradation of solar cells, and damage to sensitive instruments. Any spacecraft crossing the interstellar void would need substantial radiation shielding, and that shielding adds mass, and mass is the enemy of speed, which brings us right back to the fundamental problem. Then there is the dust problem, and this one is truly terrifying. I mentioned that interstellar space contains tiny grains of dust. At normal speeds, these grains are completely harmless. A dust grain measuring a fraction of a millimeter is not going to hurt anything if it is drifting slowly through space. But if you are traveling at a significant fraction of the speed of light, as any practical interstellar mission must, the physics change dramatically. A grain of dust that you would not even notice at walking speed becomes a devastating projectile when you are moving at 20% of the speed of light. At that speed, even a grain weighing a fraction of a milligram carries kinetic energy equivalent to a small bomb. The equation is simple but brutal. Kinetic energy equals 1/2 times mass times velocity squared. When velocity is measured in tens of thousands of kilometers per second, even tiny masses carry enormous energies. A grain of sand hitting your spacecraft at 20% of light speed would release energy comparable to a small nuclear explosion. And you cannot dodge these grains. You cannot see them coming. They are too small and you are moving too fast. Any interstellar spacecraft traveling at high speed would need either extremely robust shielding at the front, some kind of forward deflection system, or the ability to absorb impacts without catastrophic failure. This is one of the many engineering challenges that makes interstellar travel not just difficult, but genuinely dangerous. Before we go further, let us also talk about the outer boundary of our own solar system, because there is a vast, mysterious region that stands between us and the interstellar medium. This region is called the Oort cloud, and it is our solar system's last frontier. The Oort cloud is a hypothesized spherical shell of icy objects that surrounds our solar system at enormous distance. Its inner edge is thought to be at roughly 2,000 AU from the Sun, and its outer edge may extend to 100,000 AU or even further, perhaps as far as 1 to 2 light years. For reference, Pluto is at about 40 AU. The Oort cloud, at its outermost extent, may reach almost halfway to Proxima Centauri. It is thought to contain trillions of icy bodies, remnants from the formation of the solar system that were flung outward by gravitational interactions with the giant planets. These are the source of long-period comets, those visitors from the deep freeze that occasionally fall inward and grace our skies with their tails. But here is the remarkable thing. We have never directly observed the Oort cloud. It is a theoretical construct, inferred from the orbits of long-period comets, but never seen. The objects within it are too small, too far, and too faint for our current telescopes to detect. Even Voyager 1, after over 47 years of travel, has not reached the inner edge of the Oort cloud. It will not reach it for another 300 years. Passing through the entire Oort cloud and emerging into true interstellar space would take Voyager approximately 30,000 years. Think about that. Just getting through our own solar system's outermost boundary takes 30,000 years at current spacecraft speeds. And then the real journey begins. The interstellar void may also contain objects we have not yet discovered, rogue planets, worlds that have been ejected from their parent star systems and now drift through the galaxy without a sun, are thought to be extremely common. Some estimates suggest there may be billions or even trillions of rogue planets in our galaxy alone, outnumbering stars. Some of these could be lurking in the space between our solar system and Proxima Centauri, invisible and unknown. Brown dwarfs, objects too large to be planets, but too small to sustain hydrogen fusion and truly become stars, could also be drifting out there in the dark. In recent years, surveys like WISE, the Wide Field Infrared Survey Explorer, have searched for nearby brown dwarfs, and while several have been found, the space between us and Alpha Centauri remains, as far as we know, overwhelmingly empty. But the possibility that something unknown lurks in that void, an undetected object we have never seen, is both exciting and slightly unsettling. Navigation in this void presents its own unique challenges. On Earth, you can navigate by landmarks, by GPS satellites, by the stars above you. In interstellar space, you have no GPS, no landmarks, no nearby reference points. The stars themselves are your only guide, and while they provide a fixed reference frame over short timescales, navigating with precision over distances of trillions of kilometers requires extraordinary accuracy. A tiny error in trajectory, a deviation of a fraction of a degree, could mean missing your target star system entirely. At the distance of Proxima Centauri, an error of 1 arc-second 1/3600th of a degree would mean missing by roughly 300 billion kilometers. That is about twice the distance from the Sun to Pluto. Miss by 1 arc-second, and you sail right past the entire Alpha Centauri system without getting remotely close to anything. Navigation would need to be corrected en route, using observations of nearby stars and possibly pulsars, those rapidly rotating neutron stars that emit regular pulses of radiation like cosmic lighthouses. Pulsar-based navigation has been proposed as a system for interstellar travel, using the unique timing signatures of multiple pulsars to triangulate position with extraordinary precision. But this technology is still in its infancy. And then there is the communication problem. At the speed of light, a message from Proxima Centauri takes over 4 years to reach Earth. There is no way around this. No faster communication method exists, or is permitted by the laws of physics as we understand them. A spacecraft halfway between here and there would experience a 2-year communication delay in each direction. Send a message reporting a problem, wait 4 years for a response. That is not a conversation. That is a monologue with an echo. Any interstellar spacecraft would need to be almost entirely autonomous, capable of making its own decisions, handling its own emergencies, navigating its own course. It could not rely on mission control. Mission control would be years away, watching events that happened in the past, sending instructions that would not arrive until the future. This level of autonomy requires artificial intelligence far beyond what we currently possess, or at least far beyond what we have tested in the harsh environment of deep space. The spacecraft would, in a very real sense, be on its own, an island of warmth and purpose in an infinite ocean of cold nothing. Now I want to shift gears and talk about something that I think is the most fascinating part of this entire topic. If the problem is that the gap is too vast for our current technology, the natural question is, what are we going to do about it? What options does humanity have? What ideas have our brightest minds proposed for crossing this seemingly uncrossable void? And the answer, I am happy to report, is that we have a lot of ideas. Some of them are practical. Some of them are wild. Some of them sound like science fiction. And some of them sound like the fever dreams of a physicist who has had too much coffee at 3 a.m. But all of them are grounded in real physics, and all of them represent humanity's refusal to look at an impossible problem and simply give up. Let us go through them all, from the mundane to the miraculous. We should start with what we have right now. Chemical rockets. This is the technology that took us to the moon, that launches satellites into orbit, that powers every spacecraft currently flying. Chemical rockets work by burning fuel, either solid or liquid, to create hot gases that are expelled at high speed from a nozzle. By Newton's third law, the expulsion of mass in one direction pushes the rocket in the other direction. It is conceptually simple and practically proven. Chemical rockets have a long and glorious history. They have taken humans to the moon and brought them back. They have sent probes to every planet in our solar system. They are the workhorses of the space age. But for interstellar travel, they are utterly, fundamentally, irredeemably useless. The reason comes down to something called the Tsiolkovsky rocket equation, and understanding it is crucial to understanding why interstellar travel is so hard. The rocket equation, in its simplest form, tells you the relationship between the speed you can achieve, the exhaust velocity of your rocket, how fast the propellant comes out, and the ratio of your initial mass to your final mass without tool. The key insight is that this relationship is logarithmic. That means that to double your speed, you don't need twice as much fuel, you need to square your mass ratio. To triple your speed, you need to cube it. The fuel requirements grow exponentially with the desired speed. For chemical rockets, the exhaust velocity is typically around 3 to 4.5 kilometers per second. This is determined by the chemistry of the fuel and oxidizer, and there are hard physical limits on how high it can go. The most energetic chemical reaction we can use in a rocket, hydrogen burning with oxygen, gives an exhaust velocity of about 4.5 kilometers per second. That is the ceiling. We cannot go higher with chemistry. Now, to reach even 1% of the speed of light, which is 3,000 kilometers per second, using a chemical rocket with an exhaust velocity of 4.5 kilometers per second, the rocket equation tells us that the mass ratio would need to be e raised to the power of 3,000 divided by 4.5, which is e to the power of 667. This is a number so large that it is meaningless. The mass of fuel required would exceed the mass of the observable universe many times over. This is not a metaphor. This is not an exaggeration. You would literally need more fuel than there is matter in the entire observable universe to accelerate a single kilogram to 1% of light speed using chemical rockets. And 1% of light speed would still take over 400 years to reach Proxima Centauri. Chemical rockets are not going to get us to the stars. Not ever. This is not an engineering limitation that we can overcome with better designs. It is a fundamental physical limitation imposed by the energy density of chemical bonds. We need something entirely different. The next step up is ion propulsion, also known as electric propulsion. Ion drives work by using electricity, typically from solar panels, to ionize a propellant like xenon gas and then accelerate those ions to very high speeds using electric fields. The exhaust velocity of an ion drive is much higher than a chemical rocket, typically 20 to 50 kilometers per second, about 10 times better. And ion drives are extremely fuel efficient. The Dawn spacecraft used ion propulsion to visit the asteroid Vesta and then travel on to the dwarf planet Ceres, a feat that would have been impossible with chemical propulsion alone. However, ion drives have a critical weakness. Their thrust is incredibly low. The Dawn spacecraft's ion engine produced a maximum thrust of about 90 millinewtons. That is roughly the force of a sheet of paper resting on your hand. It is barely perceptible. Ion drives achieve their high speeds by running continuously for months or years, gradually building up velocity with their tiny but persistent push. For interstellar travel, even with their higher exhaust velocity, ion drives are still far too slow. The best-case scenario with ion propulsion might reduce the travel time to the nearest star from 73,000 years to perhaps 20,000 to 30,000 years. An improvement, certainly, but still utterly impractical for any mission we would want to complete within a human lifetime, or even within the lifetime of a civilization. Nuclear thermal propulsion is the next rung on the ladder. In a nuclear thermal rocket, instead of burning chemical fuel, you pass a propellant, usually hydrogen, through a nuclear reactor. The reactor heats the hydrogen to extremely high temperatures, and the hot gas is expelled through a nozzle at high speed. The exhaust velocity of a nuclear thermal rocket is about twice that of the best chemical rockets, around 8 to 9 kilometers per second. This technology is not theoretical. It was actually built and tested. In the 1960s and early 70s, NASA and the Atomic Energy Commission ran the NERVA program, Nuclear Engine for Rocket Vehicle Application. They built and tested nuclear thermal rocket engines that worked exactly as designed. The program was cancelled for budgetary and political reasons, not because of any technical failure. Nuclear thermal rockets would be excellent for missions to Mars and the outer solar system, roughly halving travel times compared to chemical rockets. But for interstellar travel, doubling the exhaust velocity barely makes a dent. You would still need travel times measured in tens of thousands of years. Nuclear thermal propulsion is a stepping stone, not a solution. However, it is worth noting that interest in nuclear thermal propulsion has recently been revived. The DARPA Draco program, demonstration rocket for agile cislunar operations, is actively working to test a nuclear thermal rocket engine in space within the next few years. This is real, funded, ongoing work, and while it will not get us to the stars, it will make us better at moving around our own solar system, which is a necessary first step. Now we get to the good stuff. The ideas that start to sound like science fiction, but are grounded in real peer-reviewed physics. And the first of these is the most gloriously insane engineering concept ever seriously studied by credible scientists. It is called Project Orion, and it proposed getting to the stars by throwing nuclear bombs behind your spaceship and riding the shockwaves. I am not making this up. This was a real project, funded by the United States government, studied from 1958 to 1965 by some of the most brilliant physicists and engineers of the 20th century. The lead scientists were Ted Taylor, one of America's most creative nuclear weapons designers, and Freeman Dyson, one of the greatest theoretical physicists of the 20th century. The concept was beautifully simple. Build a large, sturdy spacecraft with a massive pusher plate at the rear. Behind the pusher plate, eject small nuclear bombs, one at a time. Each bomb detonates a short distance behind the plate. The plasma from the explosion hits the plate, and the impulse pushes the spacecraft forward. Then you eject another bomb, and another, each one giving you another kick. The nuclear explosions provide enormous amounts of energy in a compact, controllable form, and by riding a series of these explosions, the spacecraft could theoretically be accelerated to speeds far beyond anything chemical or nuclear thermal rockets could achieve. The physics of Project Orion is sound. Freeman Dyson himself did the calculations and confirmed that the concept was feasible. Small-scale tests using conventional explosives were conducted and proved the pusher-plate concept worked. A spacecraft using nuclear pulse propulsion could potentially reach 3 to 5% of the speed of light, depending on the design and the number of bombs carried. At 3% of light speed, the travel time to Proxima Centauri would be about 140 years. At 5%, about 85 years. These are enormous travel times by human standards, but they are the first numbers in our entire discussion that are even remotely within the realm of human civilization. 140 years is about 5 or 6 human generations. It is less time than has elapsed since the American Civil War. It is conceivable. It is not easy, it is not comfortable, but it is conceivable. The original Orion designs ranged from relatively modest vehicles to truly massive spacecraft. The most ambitious designs envisioned a ship several hundred meters in diameter, weighing millions of tons, capable of carrying entire cities worth of people and supplies. This was not a fragile little probe. This was a battleship of the cosmos, designed to muscle its way to the stars through sheer brute force. And the most remarkable thing about Project Orion is that it could have been built with 1960s technology. The nuclear bombs existed. The materials for the pusher plate existed. The engineering was challenging but not impossible. It could have been humanity's first realistic starship. So why was it cancelled? 2 reasons. First, the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear explosions in space, made it illegal to actually use the propulsion system. You cannot test nuclear pulse propulsion without detonating nuclear weapons in space, and international law forbids it. Second, the political and environmental concerns of launching a spacecraft propelled by nuclear explosions, even from a remote location, were enormous. The risk of a launch failure that would scatter nuclear material across a wide area was deemed unacceptable, and so Project Orion was shelved. The most promising near-term option for interstellar travel was killed not by physics, not by engineering, but by politics and treaties. There is a deep irony here. The same nuclear weapons that could destroy civilization on Earth could also be the key to taking civilization to the stars. The instruments of our potential annihilation are also, perhaps, the instruments of our salvation. But we have chosen, for very understandable reasons, to keep those instruments locked away. Following in Orion's footsteps, the British Interplanetary Society conducted a study from 1973 to 1978, called Project Daedalus. Daedalus took the nuclear pulse concept and refined it, replacing fission bombs with fusion pellets. The concept was an unmanned probe that would travel to Barnard's star, about 6 light-years away, using a 2-stage nuclear fusion pulse engine. Small pellets of deuterium and helium-3 would be injected into a reaction chamber and ignited by electron beams, creating miniature fusion explosions that would provide thrust. The Daedalus design would accelerate for about 2 years, reaching a top speed of approximately 12% of the speed of light, and then coast for about 46 years before arriving at its destination. The total travel time would be approximately 50 years. 12% of light speed. That is an extraordinary number. It would cross the distance to Proxima Centauri in about 35 years. This is within a human lifetime. A scientist who was 20 years old at launch could potentially still be alive when the probe arrived at its destination. The data sent back at the speed of light would arrive 4 more years after that, but still, a single human life could span the entire mission. The problem with Daedalus was, and remains, its fuel. Helium-3 is extremely rare on Earth. The primary proposed source was the atmosphere of Jupiter, where helium-3 exists in larger quantities. The mission would require 20,000 tons of helium-3 pellets, and mining this amount from Jupiter would require an industrial infrastructure in the outer solar system that we are centuries away from developing. Daedalus was physically feasible, the physics worked, but it required an engineering and industrial base far beyond our current capabilities. Project Longshot, studied by the US Naval Academy in 1987 and 1988, was a similar concept but aimed for a more practical design. It proposed a 133-ton unmanned probe using nuclear fusion propulsion to reach Alpha Centauri in about 100 years at 4.5% of the speed of light. The design used a more realistic fuel mix and tried to stay closer to near-term engineering capabilities, though it still required advances in fusion technology that we have not yet achieved. All three of these nuclear propulsion concepts, Orion, Daedalus and Longshot, share a common denominator. They all recognize that nuclear energy, whether from fission or fusion, provides the only known energy density high enough to make interstellar travel possible within reasonable timeframes. Chemical bonds simply do not contain enough energy. Nuclear reactions, which tap into the strong nuclear force rather than the electromagnetic force, release about 1,000,000 times more energy per kilogram of fuel. This million-fold improvement is exactly what is needed to bring interstellar travel times down from millions of years to merely decades or centuries. But there is a propulsion concept that goes even further than nuclear fusion, one that taps into the most energetic reaction in all of physics: antimatter propulsion. Antimatter is the mirror image of normal matter. For every particle of normal matter, there exists an antiparticle with the same mass but opposite charge. When a particle of matter meets its corresponding antiparticle, they annihilate each other completely, converting 100% of their combined mass into energy according to Einstein's famous equation E equals m². Compare this to nuclear fission, which converts about 0.1% of mass to energy, or nuclear fusion, which converts about 0.7%. Antimatter annihilation converts 100%. It is the most efficient energy release physically possible. The numbers are staggering. 1 gram of antimatter annihilating with 1 gram of matter would release approximately 1.8 times 10 to the 14 joules of energy. That is equivalent to about 43 kilotons of TNT, roughly 3 times the energy of the bomb that destroyed Hiroshima. A few kilograms of antimatter, combined with an equal mass of matter, could theoretically provide enough energy to propel a spacecraft to the nearest star. The fuel requirements for an antimatter rocket would be measured in kilograms rather than the thousands of tons required for fusion propulsion. It is the dream fuel, the ultimate propellant, the holy grail of rocket science. So why are we not building antimatter rockets right now? 2 problems, and they are both devastating. First, we cannot produce antimatter in anywhere near the quantities needed. The total amount of antimatter ever produced by all the particle accelerators in the world combined is measured in nanograms, billionths of a gram. At current production rates and costs, producing 1 gram of antimatter would cost on the order of $60 trillion and take millions of years of continuous production with current facilities. This is not a problem that will be solved by incremental improvements. It requires a fundamental revolution in particle physics and energy technology. Second, even if you could produce antimatter, you have to store it. Antimatter annihilates on contact with any normal matter. You cannot put it in a bottle. You cannot put it in a tank. You cannot let it touch anything, ever, or it explodes. Current storage methods use magnetic traps called penning traps that can contain tiny amounts of antimatter using magnetic fields. But scaling these up to store kilograms of antimatter is a challenge so far beyond our current technology that it borders on fantasy. Antimatter propulsion remains theoretically the best possible rocket technology, but practically, it is probably centuries away at minimum. Now I want to talk about an idea that is fundamentally different from all of the above. Everything we have discussed so far is a rocket of some kind, a vehicle that carries its energy source and propellant with it. But what if you left the energy source at home and just pushed the spacecraft from behind? This is the concept behind light sails and laser propulsion, and it is the basis for what I consider the most exciting and realistic near-term interstellar mission concept, breakthrough starshot. Breakthrough starshot was announced in 2016 by billionaire investor Yuri Milner, with support from the late Stephen Hawking and Mark Zuckerberg, among others. The concept is radical in its simplicity and ambition. Build a very small, very light spacecraft, something about the size of a postage stamp and weighing only a few grams. Attach it to a thin, highly reflective light sail a few meters across. Then, from the ground or from Earth orbit, fire an enormously powerful laser array at the sail. The photons from the laser striking the reflective surface of the sail transfer their momentum to the spacecraft, pushing it forward. With a sufficiently powerful laser, say 100 gigawatts, the tiny spacecraft could be accelerated to 20% of the speed of light within minutes. 20% of the speed of light. That is 60,000 kilometers per second. At that speed, the trip to Proxima Centauri would take approximately 20 years. 20 years. Not 73,000 years. Not 7,000 years. 20 years. A probe launched when a child is born could arrive at the nearest star before that child is old enough to have graduated from college. The beauty of this concept is that it separates the energy source from the spacecraft. The laser array stays on Earth or in Earth orbit, where it has access to virtually unlimited energy. The spacecraft does not need to carry any fuel at all, it just needs to be light, reflective and durable. This is why the spacecraft is so small, just a few grams. The less it weighs, the faster the laser can push it. A gram-scale spacecraft pushed by a 100 gigawatt laser for a few minutes can reach speeds that would be utterly impossible for any rocket, no matter how advanced. Of course, the challenges are immense. Building a 100 gigawatt laser array would require a phased array of individual lasers working in perfect synchronization, and the total power output would be roughly equivalent to the entire power output of a medium-sized country. The laser would need to maintain focus over millions of kilometers as the sail recedes, requiring adaptive optics of extraordinary precision. The sail material needs to reflect the laser light with near-perfect efficiency, because any absorbed light would instantly vaporize the gossamer-thin material. The spacecraft, weighing only grams, needs to contain a camera, a communication system, a power source, navigation sensors, and a computer, all miniaturized to a degree far beyond current technology, but not beyond what engineers believe is possible in the coming decades. And then there is the dust problem again. At 20% of the speed of light, even microscopic dust grains become lethal projectiles. The spacecraft would need some form of shielding, or it would need to be robust enough to survive impacts, or the mission designers would need to accept that some spacecraft would be destroyed en route and launch thousands of them to ensure some survive. In fact, launching thousands is part of the current plan. The gram-scale spacecraft are so small and cheap that you could manufacture them by the thousands and launch swarm after swarm, knowing that even if many are destroyed by dust impacts, enough would survive to complete the mission. The biggest limitation of Breakthrough Starshot is that it is a flyby mission. The spacecraft has no way to slow down. There is no laser at the destination to decelerate it. It will blast through the Proxima Centauri system at 20% of the speed of light, getting only a few hours to observe the star and its planets up close before it has passed through, and is flying away into the void on the other side, never to return. But even a few hours of close-up observation at that speed, with the right instruments, could return more data about Proxima Centauri and its planets than centuries of observations from Earth. One photograph of Proxima Centauri B's surface, even a blurry one, would be worth more than 1,000 theoretical papers. It would be the first time humanity has ever seen another star system up close, and the data would travel back to Earth at the speed of light, arriving about 4 years after the flyby. 20 years of travel, a few hours of observation, 4 years for the data to come home. Within about 25 years of launch, we could have our first close-up image of a planet orbiting another star. This is not science fiction. This is funded research, with real engineers working on real prototypes right now. The The target date for a possible launch is somewhere in the 2040s to 2050s. Some of the people reading or watching this right now could live to see it happen. Let me also mention the Bussard ramjet, because it is one of the most beautiful and tragic ideas in the history of interstellar propulsion concepts. In 1960, physicist Robert Bussard proposed a spacecraft that would scoop up hydrogen from the interstellar medium as it flew and use that hydrogen as fuel for a fusion reactor. The concept was elegant. You would not need to carry all your fuel with you, because space itself would be your fuel tank. The interstellar medium contains hydrogen, and if you had a large enough magnetic funnel to scoop it up and a powerful enough fusion reactor to burn it, you could theoretically accelerate continuously for as long as you wanted. The Bussard ramjet quickly became a staple of science fiction, appearing in novels and stories as a practical method of interstellar travel. Unfortunately, subsequent analysis revealed fatal flaws. The interstellar medium is so thin that the scoop would need to be hundreds of kilometers across to collect enough hydrogen for useful thrust. And the process of scooping up matter from the interstellar medium at high speed actually creates more drag than the fusion engine can overcome. The scoop slows you down more than the engine speeds you up. You would literally be better off with no engine at all, just coasting. The Bussard ramjet in its original form does not work. Various modifications have been proposed, but none have fully solved the drag problem. It remains one of science fiction's most beloved and most sadly impractical concepts. Now let us venture into truly exotic territory. Let us talk about the Alcubierre warp drive. In 1994, Mexican physicist Miguel Alcubierre published a paper that sent shockwaves through the physics community. He showed that within the framework of general relativity, Einstein's theory of gravity, it was theoretically possible to construct a warp bubble around a spacecraft that would compress space in front of the craft and expand space behind it. The spacecraft itself would not move through space at all. Instead, space itself would move, carrying the spacecraft along like a surfer on a wave. Because the spacecraft is not actually moving through space in its local frame of reference, it would not violate Einstein's speed limit. The speed of light is the speed limit for objects moving through space, but there is no known speed limit on how fast space itself can move. Indeed, space is already moving faster than light at the edges of the observable universe due to cosmic expansion. Alcubierre showed that, on paper, a spacecraft using such a warp bubble could effectively travel faster than light without actually breaking any laws of physics. The reaction in the physics community was electric. Here was a peer-reviewed paper, published in a respected journal, by a legitimate physicist, showing that faster-than-light travel was not prohibited by general relativity. However, the excitement was tempered by the requirements. Alcubierre's original calculations showed that creating the warp bubble would require a form of matter with negative energy density, sometimes called exotic matter. The amount of exotic matter needed was staggering, equivalent to the mass energy of the planet Jupiter. Worse, negative energy density matter has never been observed to exist in any form that could be gathered, stored, or used as a construction material. The Casimir effect demonstrates that negative energy densities can exist in quantum mechanics on incredibly tiny scales, but scaling this up to create a warp bubble around a spacecraft is a completely different challenge. In the years since Alcubierre's paper, various physicists have worked on optimizations. Harold Sonny White at NASA's Johnson Space Center proposed modifications to the warp bubble geometry that could reduce the energy requirements by many orders of magnitude. Instead of Jupiter's mass energy, White's modifications suggested the energy required could be reduced to something on the order of the mass energy of the Voyager 1 spacecraft, about 700 kilograms. This is still a staggering amount of energy, equivalent to the total energy release of thousands of nuclear bombs, but it is at least a finite, conceivable number rather than the mass of a planet. In 2021, physicist Eric Lentz published a paper proposing a class of warp drive solutions that might not require exotic matter at all, using positive energy density configurations instead. This generated enormous excitement and equally enormous skepticism. The debate continues. The honest truth about the Alcubierre warp drive is this: the mathematics permits it, but we have no idea if physics actually allows it. General relativity says the geometry of such a bubble is possible, but general relativity is a classical theory. It does not account for quantum effects, and when you try to apply quantum mechanics to warp drive scenarios, all sorts of problems arise, including potential instabilities, horizon problems, and questions about causality. We do not yet have a theory of quantum gravity that could definitively tell us whether a warp drive is possible or impossible. It remains in a tantalizing limbo, neither proven possible nor proven impossible. If it is possible, it changes everything. If you can distort space itself to travel faster than light, the stars are not just reachable, they are close. Proxima Centauri becomes a day trip, the galaxy becomes a neighborhood, the universe opens up like a flower. But this is a very big if, and no honest physicist will tell you they know which way it will go. Given the uncertainty of exotic propulsion methods, some thinkers have taken a different approach entirely. Instead of trying to go fast, they ask, what if we just accept that the journey is long and design for it? This is the concept of the generation ship, and it is perhaps the most human solution to the interstellar travel problem. A generation ship is exactly what it sounds like. A spacecraft so large, so self-sufficient, and so carefully designed that it becomes a world unto itself. People are born on this ship, they live their entire lives on this ship, and they die on this ship. It is their children, or their grandchildren, or their great-great-great-grandchildren who eventually arrive at the destination. The original passengers never see the new star. They are the first generation of a lineage that will span centuries in the void between stars. If a generation ship travelled at 1% of the speed of light, which is roughly 3,000 kilometers per second, a speed ambitious but conceivably achievable with advanced nuclear propulsion, the journey to Proxima Centauri would take approximately 425 years. That is roughly 15 to 20 human generations. The ship would need to sustain a viable human population for 4 centuries, providing food, water, air, gravity, radiation protection, medical care, education, governance, culture and purpose. The engineering challenges are formidable. The ship would need to be enormous, possibly kilometers in length, to house sufficient agricultural space, living quarters, and life support systems. Artificial gravity would likely be provided by rotating sections, following the design principles of the O'Neill cylinder concept. The ecosystem would need to be closed loop, recycling all waste back into usable resources with near-perfect efficiency. Radiation shielding would need to be comprehensive, possibly using meters thick water or regolith surrounding the hull. The energy requirements for lighting, heating and operating all ship systems for centuries would be immense, likely requiring nuclear fusion reactors that run continuously for the entire journey. But the engineering challenges, as difficult as they are, might be the easy part. The social and psychological challenges are arguably even greater. How do you maintain a functioning society for 400 years in a metal tube? How do you prevent social collapse, revolution, or stagnation? How do you ensure that Generation 15 still remembers and cares about the mission that Generation 1 started? How do you educate children who will never see a sky, never feel wind on their faces, never swim in an ocean? How do you handle crime, mental illness, religious schisms, political disputes? How do you maintain genetic diversity in a small population without inbreeding? How do you keep the ship's technology functioning when the engineers who built it died centuries ago and their knowledge has been passed down through a game of generational telephone? These are not idle questions. They are fundamental challenges that would need to be solved before any generation ship could be launched with a reasonable expectation of success. Entire fields of study, from sociology to psychology to ecology to political science, would need to contribute to the design. A generation ship is not just an engineering project, it is a civilization project. And then there is the cruelest irony of the generation ship concept. What happens if, during the 400-year journey, the civilization back on Earth develops faster propulsion technology? What if, 200 years into your journey, a ship passes you that left Earth 190 years after you did, traveling at 10% of the speed of light instead of 1%? They arrive at the destination before you. The world you were traveling to has already been settled by the time you arrive. Your 400-year odyssey, the sacrifices of 15 generations, rendered unnecessary. Your ship becomes a time capsule, a monument to a technology that was already obsolete before the journey was half over. This scenario is sometimes called the incessant obsolescence postulate, and it raises profound questions about when the right time to launch such a mission would be. Launch too early, and you waste the lives of generations on a journey that faster technology will supersede. Launch too late, and you may miss a window of opportunity, or civilization may collapse before the mission begins. There is, theoretically, an optimal time to launch, a point at which the rate of improvement in propulsion technology has slowed enough that the risk of being overtaken is minimal. But calculating this optimal time requires predicting the future of technology, which is about as reliable as predicting the weather a century from now. There is another variant of the slow ship concept, the sleeper ship. Instead of living out normal lives during the centuries-long journey, passengers would be placed in some form of suspended animation, essentially frozen or metabolically slowed, and revived upon arrival. This eliminates many of the social and psychological problems of the generation ship. You do not need to maintain a functioning society for centuries because most of the passengers are sleeping. You do not need to grow food or recycle waste for thousands of people because they are not consuming anything. You do not need to worry about cultural drift or political upheaval because everyone is unconscious. The challenge, of course, is that we cannot currently freeze and revive human beings. Cryonics, the practice of preserving bodies or heads at extremely low temperatures in the hope of future revival, is practiced by a small number of organizations, but no one has ever been successfully revived after cryopreservation. The fundamental problem is ice crystal formation. When cells freeze, water inside them forms ice crystals that puncture cell membranes and destroy tissue. A technique called vitrification, which involves replacing the body's water with cryoprotectant chemicals that solidify into a glass-like state without forming crystals, has shown some promise. Small biological samples, including insect larvae and small pieces of tissue, have been successfully vitrified and revived. In recent years, researchers have vitrified and successfully rewarmed a rabbit kidney, which maintained its function after being transplanted. But scaling from a kidney to an entire human body is an enormous leap. Every organ, every tissue, every cell would need to be uniformly vitrified and then uniformly rewarmed, without any part of the body thawing unevenly and forming ice crystals. It is possible that this technology will be developed eventually, but it is not imminent. Interestingly, nature provides some inspiration. The wood frog, found in North America, survives being frozen solid every winter. Up to 65% of its body water freezes, its heart stops, its brain shows no activity, and by every normal definition, the frog is dead. But when spring arrives and temperatures rise, the frog thaws, its heart restarts, and it hops away as if nothing happened. The wood frog achieves this through a combination of cryoprotectants, primarily glucose, that it floods into its cells before freezing begins. Understanding how the wood frog survives may one day help us develop human cryopreservation techniques. Other organisms, including certain species of insects, fish, and even some turtles, have similar freeze tolerance mechanisms. Nature has solved this problem multiple times, for small organisms at least, suggesting it is not physically impossible, just biologically challenging. If we could combine a sleeper ship with moderate propulsion technology, say 5 to 10% of light speed, we could potentially send humans to the nearest star in about 40 to 85 years, with the passengers sleeping through the entire journey and waking upon arrival. This is the scenario depicted in many science fiction films, from Alien to Passengers to Interstellar, and while it remains firmly in the realm of future technology, it is not physically impossible. It requires advances in two separate fields, propulsion and cryobiology, and if both are achieved, interstellar travel becomes something that individual humans, not just their distant descendants, could experience. Now I want to pause here and do something important. I want to talk to you directly for a moment. If you have made it this far into this video, you are clearly someone who cares about these big questions. You are someone who looks up at the sky and wonders. You are someone who is not content to just live on the surface of things, but wants to dig deeper, to understand the universe on a level that most people never attempt. And that is exactly the kind of person this channel is for. So if you are enjoying this deep dive, if your brain is buzzing with ideas and questions, take a moment to hit that subscribe button. Leave a comment telling me which propulsion method you think has the most promise. Do you think breakthrough starshot is our best bet? Are you holding out hope for the warp drive? Or do you think the generation ship, with all its challenges, is the most realistic path? I genuinely want to know what you think, and I read every single comment. Now let us keep going, because we have covered the engineering, but we have not yet confronted the deeper implications of what this gap means. Let me take you now to a place that is not physical, but philosophical, because the gap between us and the nearest star is not just a problem of engineering and physics, it is a problem of meaning. It challenges everything we think we know about our place in the universe and our future as a species. And if we are going to truly understand this gap, we need to go beyond the numbers and into the realm of ideas. Let us start with perspective. Everything we have talked about so far, all those terrifying distances and impossible travel times, all of that was about reaching the nearest star. Proxima Centauri is not a star chosen for its importance or its interest. It is simply the star that happens to be closest. It is the absolute minimum challenge. The shortest possible interstellar journey. If we were to make a list of all the stars in our galaxy ranked by distance from Earth, Proxima Centauri would be number 1. It is the easiest target. And it is, as we have discussed at length, almost inconceivably far away. Now consider this. Our galaxy, the Milky Way, contains an estimated 200 to 400 billion stars. Proxima Centauri is one of them. The Milky Way galaxy is approximately 100,000 light-years in diameter. If the 4.24 light-year gap to Proxima Centauri is an impossible chasm, what do we make of a galaxy that is 100,000 light-years across? At the fastest speed we have discussed seriously, 20% of light speed from breakthrough starshot, crossing the entire galaxy would take 500,000 years. 500,000 years. Homo sapiens has existed for about 300,000 years. Crossing our own galaxy would take longer than our species has been alive. And the Milky Way is just one galaxy among trillions. The nearest large galaxy to ours, the Andromeda galaxy, is about 2.5 million light-years away. At 20% of light speed, the journey would take 12.5 million years. At 1% of light speed, 250 million years. These numbers are so large that they lose all connection to human experience. They are durations that span geological ages, evolutionary epochs, mass extinctions, and the observable universe itself. The sphere of space from which light has had time to reach us since the Big Bang is approximately 93 billion light-years in diameter. The light from the most distant objects we can see left its source over 13 billion years ago. And due to the expansion of the universe, those objects are now much farther away than 13 billion light-years. The universe is expanding, and it is expanding at an accelerating rate. This means that distant galaxies are not just far away, they are getting farther away, and the rate at which they are receding is increasing over time. Beyond a certain distance, galaxies are receding from us faster than the speed of light. Not because they are moving through space faster than light, which would violate relativity. but because the space between us and them is expanding faster than light can cross it. These galaxies are beyond our reach forever. No technology, no matter how advanced, will ever allow us to visit them, because the space between us and them is growing faster than we could ever hope to cross it. The observable universe is, in a very real sense, shrinking as cosmic expansion accelerates. More and more galaxies will cross this horizon and become permanently unreachable. In the far future, trillions of years from now, an observer in the Milky Way would see an empty universe, with all other galaxies having faded beyond the cosmic horizon. We live in a brief window of cosmic history where we can still see the rich, populated universe. Eventually, even that will be taken from us. This brings us to what I consider one of the most profound questions in all of science, the Fermi paradox. Named after physicist Enrico Fermi, who reportedly posed the question during a lunchtime conversation in 1950, the Fermi paradox is simply this. Given the vast size and age of the universe, and the enormous number of stars and planets it contains, where is everybody? If life is common, if intelligence is not a unique accident, if civilizations arise on other worlds as they arose on ours, then the universe should be teeming with spacefaring civilizations. The galaxy is 13 billion years old. Even at the slow speeds we have discussed, a single civilization with modest interstellar travel capability could colonize the entire galaxy in a few million years. A blink of an eye in cosmic terms. So where are they? Where are the radio signals? Where are the megastructures? Where are the alien probes? Where is any evidence at all that anyone else is out there? There are many proposed answers to the Fermi paradox, and I do not have time to explore them all in depth here, but I want to focus on one that is directly relevant to our topic. What if the gap is the answer? What if the distances between stars are simply too vast for any civilization, no matter how advanced, to routinely cross? What if the speed of light is not just a speed limit, but a prison wall? What if every civilization in the galaxy arises on its world, looks out at the stars, calculates the distances, and realizes that the universe has given them a beautiful view of a garden they can never enter? This is sometimes called the Great Filter hypothesis, and the interstellar distance problem is one of its most compelling manifestations. Maybe the universe is full of intelligent civilizations, all trapped on their home worlds, all looking up at their night sky and wondering why nobody else seems to be there. The answer being, they are there, but they cannot reach you, and you cannot reach them. The distances have imprisoned everyone. There is something deeply unsettling about this possibility. We humans like to believe that with enough ingenuity, enough determination, enough heroic effort, we can overcome any obstacle. It is a defining feature of our species, this stubborn refusal to accept limitations. We crossed oceans that were supposed to be uncrossable. We flew when we were told we could never fly. We walked on the moon when it was supposed to be the province of gods and poets. But what if the interstellar distance problem is different in kind from all of those? What if it is not just hard, but genuinely, fundamentally impossible within the constraints of known physics? What if the speed of light is an absolute wall, and the energy requirements for even relativistic travel are simply beyond what any civilization can muster? I want to be clear, I do not think this is the case. I believe humanity will eventually find a way to cross the interstellar gap, but I want to be honest about the possibility that we might not. The universe does not owe us the ability to reach the stars. Physics has no obligation to provide loopholes that make our dreams feasible. The gap might simply be too big, and we need to sit with that possibility, feel its weight, before we can properly appreciate why the effort to cross it matters so much. Let me talk about the time problem, because it adds another layer of horror to the interstellar distance challenge. Even in the most optimistic scenarios where we develop propulsion technology capable of carrying humans to the nearest star in a reasonable time frame, we still face the fundamental limit of light-speed communication. At 4.24 light-years away, a message from a colony on Proxima Centauri b takes over 4 years to reach Earth. A reply takes another 4 years to reach the colony. This means any real-time interaction is impossible. No real-time conversations, no real-time video calls, no real-time instructions from Earth, no real-time news. A colony at Proxima Centauri would be sending messages to Earth and receiving replies that reference events that happened nearly a decade ago. "We have a medical emergency," says the colony. 4 years later, Earth receives the message. "Here is what you should do." Replies Earth. 4 years later, the colony receives the reply. 8.5 years have passed since the emergency. Either the patient recovered or they did not. The advice from Earth is about as useful as a letter from the 19th century arriving in the 21st. This communication delay has profound implications for any interstellar colony. It would be functionally independent from day one. There would be no micromanagement from Earth, no real-time support, no cultural participation in Earth's ongoing story. A colony at Proxima Centauri would need to be entirely self-governing, self-sufficient, and self-directed. It would, within a generation or two, develop its own culture, its own traditions, its own way of seeing the world. It would cease to be an extension of Earth and become something new, something alien in its own way. Humanity would not be one civilization anymore. It would be two, separated by an uncrossable communication chasm, slowly diverging like two branches of an evolutionary tree. Over centuries and millennia, the colony and the home world would become as different from each other as different species. Different languages, different cultures, different values, different physical characteristics if the gravity and radiation environment were different enough. The gap does not just separate us physically, it separates us temporally and culturally. It is a force of divergence, splitting one humanity into many. And yet there is something beautiful about this too. If humanity did spread to other star systems, even with the communication delays, even with the cultural divergence, we would be insured against extinction. Right now, all of human civilization exists on a single planet. One asteroid impact, one supervolcano, one sufficiently devastating pandemic, one nuclear war, and everything we have ever created, every symphony and sonnet and scientific discovery, could be lost forever. A civilization that has spread to multiple star systems cannot be destroyed by any single catastrophe. The loss of one world would be tragic beyond measure, but the species would survive, the culture would survive in altered form, the knowledge would survive. This is perhaps the most compelling practical argument for interstellar colonization. It is not about exploration or adventure, though those are worthy motivations. It is about survival. It is about ensuring that the flame of consciousness that flickered to life on this one small world is not extinguished by a single unfortunate event. The gap is the obstacle, but what lies on the other side of the gap is the ultimate insurance policy. I want to also address the loneliness factor, because it is something that weighs on me when I think about these distances. As far as we know, as of right now, we are alone. Not just alone on Earth, where we are clearly not alone with millions of species sharing our planet, but alone in the cosmos. We have not detected a single signal from another civilization. We have not found a single artifact. We have not seen a single indication that anyone else is out there. The universe, as far as our instruments can tell, is silent. Now, this does not mean we are alone. Absence of evidence is not evidence of absence, as the saying goes. The universe is vast, our search has been limited, and there are many reasons why we might not have detected alien signals even if they exist. But the silence is real, and it is heavy. When you combine this silence with the knowledge that even the nearest star is almost unreachably far away, a profound sense of cosmic loneliness settles in. We might be the only intelligent beings for dozens or hundreds of light years in every direction. We might be the only ones in our entire galaxy. We might be the only ones in the observable universe. We do not know. and the distances make it so that even if we are not alone, meeting our cosmic neighbours might take centuries or millennia. In the meantime, we sit here on our little blue dot, surrounded by a silence that stretches in every direction for light years upon light years upon light years. Carl Sagan captured this feeling better than anyone with his famous reflection on the pale blue dot photograph, taken by Voyager 1 in 1990 from a distance of about 6 billion kilometres. In that photograph, Earth appears as a tiny speck, less than a pixel, suspended in a beam of scattered sunlight. Sagan wrote about this image with an eloquence that I cannot match, but the core message is this: everything that has ever happened, every king and peasant, every saint and sinner, every moment of joy and sorrow has occurred on that one tiny speck, and that speck is a mote of dust suspended in a sunbeam, a tiny island in an infinite cosmic ocean. The gap between us and the nearest star is just the first tiny fraction of that ocean, and we have not even gotten our feet wet. But I promised you that this video would not just be about despair, and I intend to keep that promise. Because there is another way to look at the gap. Yes, it is terrifying. Yes, it is humbling. Yes, it challenges every instinct we have about our significance and our capabilities. But there is also something magnificent about facing an impossible challenge and refusing to look away. Every frontier humanity has ever confronted looked impossible from the near side. The Pacific Ocean, the largest body of water on Earth, was crossed by Polynesian navigators in small outrigger canoes thousands of years ago. They had no GPS, no maps, no compasses. They navigated by the stars, the waves, the flight patterns of birds. They looked at an ocean that seemed infinite, and they said, "We can cross that." And they did. The Atlantic Ocean was a barrier that separated continents for all of human history until a few hundred years ago. Everyone knew you could not cross it. The water was too deep, the storms too fierce, the distance too great. And then a few crazy sailors proved everyone wrong. The idea of human flight was considered absurd for millennia. Heavier than air flight was declared physically impossible by respected scientists. And then 2 bicycle mechanics from Ohio proved them wrong in about 12 seconds at Kitty Hawk. Going to the moon was considered a fantasy, a children's dream, a poet's metaphor. And then 12 men walked on its surface. The interstellar gap is different in degree from all of these, I acknowledge that. The distances are not merely daunting, but cosmically vast. The physics is not merely challenging, but fundamentally constraining. But I want to suggest that we are still in the early stages of understanding what is possible. Our species is only 300,000 years old. Our scientific revolution is only about 400 years old. Modern physics is barely a century old. We have been doing space travel for less than 70 years. In the context of cosmic time, we have barely blinked. We are infants, taking our first wobbling steps, looking up at a mountain and saying we can never climb that. But infants grow. They learn to walk, then to run, then to build tools, then to build machines. Give us a few more centuries of scientific progress. Give us a few more paradigm shifts in physics. Give us the discovery of some principle we do not yet understand, some aspect of nature that we have not yet noticed, some loophole in the laws of physics that we have not yet found. I am not saying we will find a warp drive or a wormhole or some other miracle technology. I am saying that the history of science is a history of discovering that the universe is stranger and more permissive than we thought. Let me bring us back to what is happening right now, in the real world, as concrete efforts are being made to inch us closer to the stars. The Breakthrough Starshot project is actively conducting research. Engineers are working on the laser array design, on the sail material, on the miniaturized electronics that would form the payload. Progress is being made on all fronts, albeit slowly. This is a project measured in decades, not years, but it is real and it is ongoing. NASA's Innovative Advanced Concepts program, known as NIAC, regularly funds studies of advanced propulsion concepts. including solar sails, electric sails, and fusion drives. The DARPA Draco program is developing nuclear thermal propulsion for near-term use in cislunar and Mars missions. The James Webb Space Telescope and future planned observatories are studying the Proxima Centauri system and other nearby star systems in unprecedented detail, characterizing exoplanet atmospheres and searching for biosignatures. If we detect signs of life on Proxima b, whether through atmospheric chemistry or some other indicator, the motivation to send a probe there would become overwhelming. Nothing accelerates technological development like a compelling reason to go somewhere. In the near term, over the next 20 to 50 years, we can expect solar sail technology to mature, with missions to the outer solar system demonstrating the principles that will eventually be used for interstellar travel. Nuclear thermal propulsion will likely be tested in space and eventually used for Mars missions, giving us experience with nuclear systems beyond Earth orbit. The miniaturization of electronics will continue its relentless march, making smaller and lighter spacecraft possible. Artificial intelligence will advance to the point where autonomous spacecraft can navigate, make decisions, and respond to emergencies without human intervention, a necessity for any interstellar probe. And our understanding of the Proxima Centauri system will improve dramatically as new telescopes come online, giving us a much clearer picture of what awaits us at the end of the journey. In the medium term, 50 to 100 years from now, it is plausible that Breakthrough Starshot or a similar project will actually launch its first interstellar probes. Tiny, gram-scale spacecraft accelerated by powerful lasers, screaming through the void at 20% of light speed. If launched in, say, 2060, they would arrive at Proxima Centauri around 2080, and their data would reach Earth around 2084. Someone born today could live to see the first close-up images of another star system. This is not a wild fantasy. It is a plausible technological roadmap based on current research trends. In this same time frame, advances in fusion energy could make nuclear fusion propulsion practical, opening the door to larger, faster probes. Space-based manufacturing using asteroid resources could provide the raw materials for truly ambitious spacecraft, and if cryopreservation technology matures, the first frozen travelers might be launched toward nearby stars, sleeping through centuries of travel in the cold dark between worlds. In the long term, 100 to 500 years from now, the possibilities expand dramatically. If fusion propulsion matures, speeds of 5 to 10% of light speed become achievable for crewed missions, bringing Proxima Centauri within a 50 to 100 year journey. Generation ships become feasible if the social and ecological engineering challenges can be solved, if some breakthrough in physics occurs, some new understanding of space-time or energy or propulsion that we cannot currently foresee, the timeline could compress even further. 500 years ago, in the early 1500s, the most advanced technology on Earth was the sailing ship and the printing press. 500 years from now, our current technology will seem equally primitive. What will we be capable of then? I cannot say. But I can say this, the gap will still be there. The physics of distance does not change, but our ability to deal with that distance will have been transformed beyond recognition. And now I want to share with you the most optimistic scenario, the one that fills me with the most wonder and hope. Throughout the history of science, the most transformative breakthroughs have come not from incremental improvements in existing technology, but from the discovery of entirely new principles. Nobody in the 1800s predicted nuclear energy because nobody knew about nuclear physics. Nobody in the 1700s predicted electronics because nobody understood electromagnetism. Nobody in the 1600s predicted that space travel was possible because nobody had the mathematical framework to describe orbital mechanics. The pattern is clear. The most important discoveries are the ones we do not see coming. They are the unknown unknowns, the things we do not know that we do not know. Right now, in the early 21st century, we understand a great deal about physics. But we also know that our understanding is incomplete. We do not have a theory of quantum gravity that unifies general relativity with quantum mechanics. We do not understand what dark matter is, despite the fact that it makes up about 27% of the mass energy of the universe. We do not understand what dark energy is, despite the fact that it makes up about 68% of the mass energy of the universe. We do not understand why the universe has more matter than antimatter. We do not understand the nature of consciousness or whether it has any connection to quantum mechanics. We do not understand the interior of black holes or what happens at the singularity. We do not understand whether our universe is one of many in a multiverse. In short, roughly 95% of the universe's mass energy content is in forms we do not understand, and some of the most fundamental questions in physics remain unanswered. Is it not at least possible, even likely, that within this ocean of ignorance lie discoveries that could change the game completely? Perhaps dark energy can be manipulated. Perhaps quantum entanglement has implications for communication or transportation that we have not yet grasped. Perhaps the theory of quantum gravity reveals new physics that makes faster-than-light travel possible in ways Alcubierre never imagined. Perhaps there are dimensions of space that we have not yet detected that could provide shortcuts between distant points. I am not saying any of these specific things will turn out to be true. I am saying that the history of science overwhelmingly suggests that our current understanding is incomplete, and that the most transformative discoveries come from the gaps in our knowledge. The gap between us and the stars is vast, but the gap in our understanding of the universe is also vast. And it is from that second gap that the bridge across the first will eventually be built.